And if you have any question, please ask me so I can answer your question. In this PDF, there are some theorems. For example, theorem 1.62. It is in the page 3 of the book. For p between 1 and infinity, C of a and b means the set of all continuous functions from a and b to c is dense in L power p of a and b. L power p of L and b means whole integrable functions with norm p. Note, the above theorem states that if f is in LP a and b, then because C of a and b is dense in LP a and b, there exists a sequence Fn in C a and b, means a sequence of continuous function from a and b which converges to f in LP metric, means the limit of f, the norm p of fn minus f approaches or goes to 0 when n goes to infinity. And because the norm p of LP is the integral of the absolute value of fn minus f power p d mu, and hold the integral power 1 over p. So this integral must be, the limit of this integral must be 0 when f approaches to infinity. Norm spaces, chapter 2. I don't know why it doesn't move to below. What? Something must be wrong. Oh, I should stop sharing. Okay. Okay, some example of norm spaces. Okay, some examples. One, the function norm from Fn to R defined by the normal x1 until xn, the n tuple x1 to xn equals the sigma absolute value of xj power 2 over sigma power 1 over 2, means the radical of the sigma, when f is R or C. This is a norm on L on f power n. We call this a standard norm on Fn. Another example of norm space, let x dimensional x equals n and the set of E1 to En be a basis for x over f. Okay, everything is okay? Okay. In this example, the dimension of x equals n, and this is a basis for x over f. Now, for any x in x, there exists unique scalars lambda 1 to lambda n, such that x equals the sigma lambda j ej, j from 1 to n. Then this function defines a norm on x by this sigma. We define the norm of x as the sigma absolute value of lambda j power 2, j from 1 to n power 1 over 2. This is also a norm on x. Another example, if n be a compact space and Cp n be the vector space of continuous f-valued functions defined on M, then the function, this function from Cfm to R defined by defined by this the norm of f, the supremum of absolute value of f of x for all x in n. This is a norm on CFN. CFN means all continuous function from n to f. F equals R or C. This is also a norm. Another example, we recall that small l power p is the vector space of all sequence xn in F such that the series absolute value of xn power p n from 1 to infinity is finite for all p from 1 to infinity, and L power infinity is the vector space of all bounded sequences in F, so that a sequence xn is it must be like this. Means the sequence belongs to L infinity, not as a subset of L infinity. We should correct this. So the sequence is in L infinity if and only if the supremum of the absolute value of xn is finite. Another example, if p is from 1 to infinity, then the norm p of the sequence xn is defined to be the series of absolute value of xn power p and from 1 to infinity, all the series power 1 over p. This is a norm on LP called a standard norm on LP. And the infinity norm of the sequence xn equals the supremum of the absolute value of xn. This is a norm on L infinity called the standard norm on L infinity. Another example, if x and y be x and y are vector spaces with the norms norm 1 and norm 2 respectively, then the Cartesian products x cross y has a norm defined by this equation. The norm of the ordered pair x and y equals the norm 1 of x plus the norm 2 of y. This is also a norm on Z as the of x. Example, x is a vector space. We can define a metric on x by this equation. D if we have a space and a metric called the metric means this is a norm. So because this metric is the metric associated with the we have a theorem here. This theorem is in the page 37 of the book. Please see this theorem. This theorem is associated with the metric from obtained from norm. Now, as a baseline, L norm 1 and norm 2, let these two norms be two norms on X. So X is a vector space with two norms, norm 1 and norm 2. We say that norm 2 is equivalent to the norm 1, or these two norms are equivalent if there exist two positive numbers m and n such that it must be m, the small m, not n, it must be a small m, capital M and a small m, such that for all x we have this these inequalities. M small m dot the norm 1 of x is less than or equal the norm 2 of x, and this is or equal norm related with this definition. I ask you okay. So for a finite dimensional vector space with norm and a basis, if another norm on X defined in example 2, norm 1 equals the, if X equals lambda j ej, j from 1 to n, as example 2, the norm 1 is the sigma of Lj, absolute value of Lj power 2, all the sigma power 1 over 2. So X is a norm space with norm. There is another norm 1. So these two norms, norm and norm 1, are equivalent. In fact, in finite dimensional vector space, any two norms are equivalent. Corollary, if there are, if there are two norms, norm 1 and norm 2, on a finite dimension. This is very important, finite dimension. It's not true for infinite dimensional vector space. But in finite dimensional vector space, any two norms are equivalent. Lemma 2.18. Let X be a finite dimensional vector space over F, and E1, En be a basis for X, and ρ1 is the norm, like in example 2. Then X is complete metric space. So for any finite dimensional vector space with norm 1 is complete. Any finite vector space with norm 1 is complete, so with any other norm is also complete. Corollary, as I said, so X with any other norm is complete, because when norm as in example 2 from X to R is equivalent to any other norm. So when V is complete with norm 1, so this is complete with any other norm. This is not true when X is infinite dimensional. This is true just for finite dimensional vector space. And norm and norm 1 be two, and D and D1 be metric space defined by D of X and Y equals the norm of X minus Y, and D1 of X and Y equals the norm 1 of X minus Y. If Xn be a sequence in X, then Xn converges to X in X and D, with this D associated with the norm, if and only if it converges to X in X and D1. D1 is the norm associated with the norm, the metric D1 is a metric associated with the norm 1. It means that if any sequence is converges in metric D, it is also converges in metric D1, or and vice versa. Another another part of this theorem B says that a sequence Xn is Cauchy in X and D if and only if it is Cauchy in X and D1. So for two equivalent norms, sequence convergence sequence are the same and Cauchy sequence are the same too. Corollary: if Y is a finite dimensional, so anything we have said is about anything we have said is about finite dimensional, and these facts are not true for infinite dimensional. So be careful, they are for just finite dimensional. If Y is a finite dimensional subspace of a norm vector space, then Y is closed. So any finite dimensional of the norm vector space are closed. The reason of this theorem is the proof is because Y is itself a dimensional normal space by this corollary. So this is closed. Lemma. If X is a norm vector space and S is a linear subspace of X, then S bar means the closure of S is also a linear subspace of X. Remark, let X and D be a metric space and E a subset of X. Then X is in E bar means the closure of E if and only if there exists a sequence Xn in E such that Xn approaches to X when n approaches to infinity. Because for two members X and Y in S bar and alpha as a scalar, there are sequences Xn and Yn in S such that they X is the limit of Xn and Y is the limit of Yn. Since X is a linear subspace, so the sum of two members of S is also in S. So Xn plus Yn must be in S. And because X plus Y equals the limit of Xn plus Yn, and this limit is in S bar. And also alpha X equals the limit of alpha Xn, and this is also in S bar. So S bar is a linear subspace. Hence, S bar is a linear subspace. Definition. Let X be a normal space and E a non-empty subset of X. Then the closed linear span of E, denoted by SPE bar. SPE means the linear span of E, and bar means the closed linear span of B. This is the intersection of all closed linear subspace of X which contains E. So this is the intersection of all F such that F is closed and F is a subspace of X and contains E. Lemma. Let X be a normal space and E a non-empty subset of X. A SP bar E is a closed linear subspace of X which contains E. B SPE bar equals SPE bar. There are two notations. First is the closed subspace of X such that contains E, but this is the space span of E bar, the closure of span of E. But here they are the same. This theorem is called Ree's lemma. Let X be a normal space, Y be a closed linear subspace of X, and Y is not X, is not equal to X, and alpha is a number, is a real number between 0 and 1. Then there exists a member, we call it X alpha, with index alpha in X such that the norm of X alpha is equal and the norm of X alpha minus Y is greater than alpha for all Y in Y. This lemma is called Ree's lemma. Another theorem: if X is an infinite dimensional vector space, so neither this set D equals the set of all X, then the norm of X is less than or equal 1, and nor K as a set of all X when the norm of X is 1 is compact. Because this is infinite dimensional, none of these sets D and K are compact. But in finite dimension, both D and K are compact, but here they are not compact. So this is because this vector space is infinite dimensional, not finite dimensional. Definition: a Banach space is a normal vector space which is complete. So any norm vector space that is complete, we call it Banach space. Under the metric associated with the norm. Theorem A: any finite dimensional vector space is Banach space. So if you know that X is a finite dimensional without vector space, without any further knowledge about the X, we say that this is Banach space. Without any further information about the X, we say that this is Banach space. B: if X is a compact metric space, or a compact metric space, C of F is a Banach space. C. If X sigma mu is a measurable space, X is a set and sigma is a field of measurable subset, and mu is a measure. So we call this triple measure space. Then L power p of X is a Banach space for all p from 1 to infinity. And a small l power p is also a Banach space for all p from 1 to infinity. These are the examples of Banach spaces. If X is a Banach space and Y is a linear subspace of X, then Y is also a Banach space if and only if Y is closed. We know that the closed subset of complete metric space are also complete. So a subspace of a Banach space is Banach space, also is a Banach space if and only if this is closed. Note that the above theorem introduces some examples. So this is a theorem, but this is also some examples of Banach spaces. Theorem. This theorem is very important. As I write here, this is very important. Let X be a Banach space and let Xn be a sequence in X. If the series of the norm of Xk, k from 1 to infinity, converges, then the series of Xk is also converges. If this series, that is a real series, of the series Xk is converges, we say that this series converges absolutely. So if a series converges absolutely, the series is also converges itself. Some exercises. There are some exercises with the solution. Let S be a subset of X and F be S and X as a sublinear subspace, sublinear space of F of X and X such that the Fp of X and S and X equals all F from S to X, such that the set of all norms of F of S for all S is bounded. Now in this exercise we should show that the norm of Fb, the norm B of F as a supreme of all F of S for all S in S is a norm. So we should show that all the conditions that must satisfy so that this be a norm. We should show that all the conditions of a norm are satisfies this equation. This is here is the solution. I left it for you to study the solution. Another example. Let X be a norm space and X is a non-zero element. So X belongs to X minus 0. So X is not 0. It means that X is not 0 and R a positive real number. Now we should find a real number alpha such that the norm of alpha X equals R. This is also the solution of this exercise. I left it to you to study the solution of the exercise, but I advise you to solve the exercise first by yourself and then see the solution. It's much better. Another problem, let Xn norm 1 and Yn norm 2 be two norm spaces. We define Z as the Cartesian products of X and Y, X cross Y. And for any member Z of Z, we define the norm of Z as the norm of x1 plus norm 1 of x plus norm 2 of y when Z equals the order pair X and Y. Now let the sequence of order pair X and Yn in Z A show that this sequence approaches to the order pair X and Y if and only if Xn approaches to X and Yn approaches to Y. B show that this sequence is Cauchy in Z if and only if Xn is Cauchy in X and Yn is Cauchy in Y. I think this is the solution of this problem. Okay, I think it is enough for now, and until the page until the page until the 2.7 until this problem. Okay. Any question? If there is any question, please ask me. And I should say that this Thursday, I mean a day after tomorrow, we won't have any lecture. And the next lecture will be the next week, Sunday. Okay? And the next week will be the last week of our lectures. But if you have any question, you can ask me by WhatsApp. Any question? No? So if there is no question, I finish the class. Goodbye.